So welcome back to one more presentation now. Uh, as I already told you, we were discussing about the sequential function charts or SFCs. I have already told you in the previous presentation itself what exactly we mean by sequential function charts, where do we use them, how to use them and all. In a very nutshell, let us go into the details of this and I would like to continue with the same example which I had mentioned in my previous presentation. You need to have the control over the traffic light signal, whereas the different lights getting blinked on, different lights getting turned on, that depends upon different conditions. The conditions are here basically the time elapse, as you know, right? So for 10 seconds one light is glowing. After another 2-3 seconds one more amber or yellow, then again for 10 more seconds or 20 seconds, whatever it is, how it is configured. Based on that, right, you have to have the green light glowing, and like that the sequence has to continue. So whenever you want to have the continuation of the sequence, right, so it is like you can see here, it will go to the start state, and in some cases you may have the process ending somewhere. Okay, so here your process, if it is ending, then you will have to indicate with an end rung or something like that, right? So basically the sequential function charts are the pictorial representation of a system's operation to show the sequence of events involved in the operation. Now there are certain important parameters which you need to understand while we draw the sequential function chart. So now suppose if I call these three, one as the state, okay, this is the first thing which you should understand in our sequential function chart, right? Then you have output, then you have transition, right? So here this transition might come before the output. Sometimes based on some output the transition might come, right? So that's why whether the transition comes here or here, it is depending upon the type of the SFCs that you are going to draw, right? So now if you look at this diagram, you have something called states here. Based on this state, right, some outputs, right? After this output there is taking place, right, or this is the transfer condition. So based on the transfer condition, again you would come across one more state, then you have one more output, one more transition. Like this it may keep going, or it may go to the initial state depending upon what kind of program that you are writing, or depending upon what kind of application you want to have from this sequential function charts, right? So now with this background, let us move on to the illustration part of it. As you can see here, the operation is described by number of separate sequentially connected states or steps. Number of separately or separate sequentially connected states or steps represented by rectangular boxes. So now the rectangular boxes, whatever we have here, right here, they represent the operation. Each connecting line between the state has a horizontal bar. Each connecting line between the states has a horizontal bar, okay, as I have already indicated there, representing the transition condition that has to be realized before the system can move from one state to another state. Now in the previous example which I have taken, what is the transition condition there? Now suppose if you want to have, see, initially let me start with a red light. Okay, I have something called a red light here. Okay, then after the red light I will have yellow light. Okay, then followed by that I need light, something like this. This is what is the traffic sequence. Now, once if you reach here, you will be made to go back to the red light condition. Okay. So now, whenever you want to transfer from a red light condition to yellow light, something must happen here, right? So what is that something is the timer operation in this case, right? So let us say that I wish to have this for say 10 seconds. Okay, I wish to have it for 10 seconds. So how do you come to know that 10 seconds has elapsed? There should be some timer. Again, of course, about the timer and all we will discuss later. That is a separate module when we take up the PLC timers, right? So there are different kind of timers which may find their usefulness in these kind of examples as well. So now, once the red light starts glowing in the beginning, your timer which was initially set for 10 seconds, it is now down counting. Once it reaches 0, once the down counting makes the timer to reach to 0, a kind of a pulse is generated or any kind of switch is activated, something like that. That is called as the, reason for the transition or the transition condition, right? So once the, timer has become 0, immediately your state is going to change, that is from red light to yellow light, right? So once the yellow light starts turned on, again your timer may be, say there may be, it is there for about say 5 seconds. Okay, your yellow light may be made to blink for about 5 seconds. So once 5 seconds is elapsed, again you will have version of the timer pulse or something like that, right? That will make you to go to the green light. Again, your green light might might be on for 10 seconds. Again, the same timer operation takes place. Once the 10 second is elapsed, so there may be one more pulse generated here, and this pulse will make your probe sequence to go back to your red light. So this is what is the thing which is explained in the form of the sentences here, nothing more than that, right? The operation is described, a number of separate sequentially connected states or steps represented by rectangular boxes. Then each connected line between the state has a horizontal bar representing the transition condition that has to be realized before the system can move from one state to another state. When the transition condition to the next state are realized, then the next state or step in the program occurs. So it need not be only the state. You please try to understand the difference between the state and step. State means a kind of output. Step means you may have some series of operations there also, so that you get the output corresponding to the second output or the second step, right? So then again you may have one more transition taking place. Either it might result in a output or there may be some sequential steps there also, depending upon what kind of application you want to realize, and you may have one output there, right? So that is the reason why it is state or step in the program that is taking place whenever the transition condition to the next state are realized, right? The process continues from one state to another until complete machine cycle is over, right? So this is what we call it as the machine cycle. This complete operation is called as the machine cycle, and the outputs or actions, this is very important, the outputs or actions at any state are represented by horizontally boxes. So now this is the box which is horizontally linked with this sequential function. Sequential functions are represented vertically one after the other, very much similar to how you draw your ladder diagram. Then any state or any action corresponding to a particular output in a particular step or in a particular stage, it is represented by horizontally linked box and occurs whenever that particular state has been realized. So now this stage or step is realized here, and accordingly you will have the output. So the timer 1 has elapsed here, example, and your amber or yellow light will glow here. Again, you will come to the next point. Here, your green light will glow here. Once you go to, suppose if it is a continuous loop, to your red light. Otherwise, it will have to stop somewhere when it is called as the final step. Okay. So these are some of the operations or some of the points to be noted whenever you have the realization of the sequential function chart. Okay, so now with we will move on to the next aspect, wherein we should be able to draw the sequential function chart for a given case or given example, and from the sequential function chart we should be able to draw the equivalent ladder diagram. So this is also important for us, because whatever the action we perform in our PLC environment, right, the industrial process or the control, ultimately whether you draw the functional blocks, whether you have the Boolean expressions, whether you have got the sequential function charts, all those must be converted into their equivalent ladder diagram, right? We have already seen, we have been familiar with how to draw the simple ladder diagrams for different functional blocks, or even for some of the simple logical or Boolean expressions. A similar way, we will proceed here also, how to draw equivalent ladder diagram given a sequential function chart, or when you have drawn a sequential function chart based on some application. Okay, so now these two diagrams are very simple to understand. Of course, in all the examples we have started with the simple illustrations before we go into the actual cases. So now as you can see from the knowledge of our previous slide, okay, so we have got a start block. Now you have got step 1 and step 0 here. You can see a step 0 and step 1. So these indicate the actions after the transitions have taken place. In any sequential function chart, the start block is represented by this kind of thing, a double line on the side of the adjacent sides, just to differentiate between it is a start block rather than it is the action block. The action blocks are there, step 0 as well as step 1, right? So now you have started some operation here. Let us say that some input here, okay, which is the transition, has made your work or your sequence of the work to move to step 0. As a result of step 0, you are some output here. So that output is out 1, as you can see, right? You have got a switch here. Once the switch is closed or once the switch is opened, that's what I mean by step 0 here. Whether the switch is opened or switch is closed, that is the action which is taking place. That results in one kind of output. That is your out 1. Okay. Now, after having got the output 1, let us say that we have got one more transition here, that is your IN2. So this may be another switch. You can, if you look at the adjacent diagram, so probably you should be able to understand what I am trying to convey here. So now your IN2 here, in this case, it happens to be, but the switch will come to action only depending upon the output 1. So some output has taken place, then only your switch IN2 will come into picture. It is not an independent switch. Please note this, right? So this IN2 will come to the action only after you have got one output from the previous transition, that is step 0, which has resulted in the output out 1. Okay, so now based on that, you have got IN2 that has resulted in one more action which is indicated by step 1 here. So this step 1 has a similar way resulted in one more output, which in my case is out 2. Okay, so now like that, see here I have got N3, one more transition, but that is meaningless because this will take my sequential function chart to an end label, right? So therefore you need not really draw the IN3 transition there. after your output 2, your task which is sequentially configured is virtually over. This is how you should be able to interpret this sequential function chart. You started with adjacent lines having double lines. Okay, adjacent square, it is having the double line. Then you start with some input that results in some kind of transition, which is step 0, which results in some kind of output, out 1. Then this output further leads to one more transition along with one more switch, that is IN2. So that will result in the transition step 1. Then it results in the output 2. Virtually after that your sequence ends. Now you should be able to realize the same thing with the help of the ladder diagram. Okay, start. Okay, it is always this junction, as you have already come across earlier. It represents a start of a new rung. So therefore start is already taken care of there. Then the input there, IN1. Okay, and you will not be specifying what exactly is your step 0. It could be an open, normally open switch, or it could be a normally closed switch there. That itself is the transition, and that transition has resulted in this output, out1. Step 0, when 1 occurs, then the step 0 is realized, and as a result of that, out 1 occurs. This is how you should be able to interpret the operation in the first rung of this ladder diagram based on the sequential function chart, right? So then you go to the next one. As I've already told you, your out 2 is dependent on two cases there. One is your out 1, then your IN2. So therefore when both hold good, when your output 1 also holds good and your input 2 also holds good, then we are realizing the step 1, right? Maybe this is going to be a closed switch now, this is going to be a closed one. Then let us say that your out 2 is going to be realized. Step 1, what you have, when the step 1 has been realized, right, that is the out 1. In fact, when the step 0 has been realized, it should have been step 0 here, right? When the step 0 has been realized, when that is when your out 1 is realized, and then you please note this, these words are very very important for us. Maybe in English we may ignore that, but in logic we cannot ignore and or all those things. So now when the step 0 is realized and the transfer into holds good, then the step 1 is realized, and accordingly your out 2 occurs. This is how you should be able to simply correlate the different actions corresponding sequential function chart and the equivalent ladder diagram. Okay, so now with this background, let us do some more aspects here. Maybe before I go into this, let me illustrate the problem here, because I have directly taken the example there. So this is one very common example which we generally come across. That is the example of a washing machine. Okay, so whenever I speak about the washing machine, right, so first I should be able to tell you what exactly is the problem definition there. Okay, now let us look into the problem definition in this way. Let me say that I have got a washing machine here. I will take the example of a washing machine. Maybe it is a semi-automatic type of the washing machine or something like that, right? Now there are different operations which are required to be realized in the washing machine, which will complete one cycle before you put the clothes inside the washing machine and before the machine is turned on. Then finally when the machine operates and your clothes are washed, right? So this is where you can make use of the sequential function charts or SFCs to illustrate the operation of the SFCs. Okay. Now here let us say that I have one operation here. You have got the drum, washing machine drum. The drum has to be filled with water. This is one requirement now. The drum has to be filled with water. Then once your drum is filled with the water, then your heater is to be turned on. The heater is to be turned on. I think it is always better you parallelly note down these things. I am spending little more time, right? So then once the temperature is reached to desired value, okay, when the temperature is reached to desired value, you have to rotate the washing machine for a specified time. So all these things are very important for me to draw the sequential function chart, right? So now once the washing machine is made to rotate for a specified period of time, then stop it. This is going to be my last operation. See, please note here, this is not the operation which has to be continuously repeated, unlike the traffic signal or the traffic light operation, right? You have the washing machine, right? You have maybe apart from whatever I have specified here, there could be several other features also in the fully automatic washing machines and all, where human intervention becomes very minimum, right? So now this is one a typical example which can be used to illustrate how you can have the sequential function charts and the corresponding ladder diagram with the help of a practical example, that is the example of a washing machine. Okay, so now if you look here, first we will try exactly we mean by this. Drum is to be filled with the water. So washing machine will be having the drum, right? When you turn on, you will listen to some kind of sound when the water is getting filled up, right? So water is filled now. Once the water is filled, how you will come to know? That is again by virtue of the different sensors. The sensors play a very important role in all these PLC operations, right? Once the drum is filled with the required amount of water, or when the water level has reached the required value or the level, okay, then the heater has to be turned on. Heater means you may wash the clothes at 40-degree temperature, 30-degree temperature, 60-degree temperature. That all depends on your requirement, right? So once the heater is turned on, you will have to wait till the temperature is reached to a desired value. Again, you may have a temperature sensor there, right? So that will indicate to what value the temperature has reached after you have turned on the heater. Then once the temperature has reached to that particular value, start rotating the washing machine for a specified period of time. 10 minutes, 15 minutes, 30 minutes, that all depends upon your requirement. Once the washing machine is made to rotate for a particular period of time, you assume that the process of washing is over and you will have to stop. So this is where you have the sequence of operation. You cannot afford to have the temperature to reach to 40-degree before your drum is filled with the water or before the heater is turned on, right? So you cannot just simply say that the process is over only by having filled the water to the required level. Every operation has to go with a particular sequence. So now it is of course a very simple example with only a 3 level of the transitions taking place here. But when you think of some industrial process, some control, you have hundreds of such operations which are required to be executed in a serial manner or in a sequential manner, right? You may have multiple outputs to be generated at a particular transition. You may have multiple branches to be activated after a particular transition takes place, right? So you may have parallel branches, you may have serial branches. We just try to imagine the kind of applications that we have in our day-to-day life which work on the sequential basis, right? So to tackle to that kind of problems, these are the basic things which we will start. You have got a washing machine, you have to fill the drum with the required level of water. Once it is filled, you have to turn on the heater. Once the temperature is reached to a desired value, then you start rotating the washing machine till your time elapse, the required time is over. So then you stop it. This is what is your problem statement here. So based on this problem, now you will have the different inputs, different transitions, different actions and different outputs. Please try to listen to these words very carefully. Inputs, transitions, actions and outputs, and based on that you will have to draw the sequence function chart, right? So now this is a simple example which I have already taken now, and for which I should be able to draw the sequential function chart. So now please look at this diagram, the sequential function chart. As usual, we start with a start block. Again, needless to mention how your start block appears to be different from your other conventional action blocks, right? I have already told you that. Now you look at the first transition which is taking place there, that is the start switch is pressed. The first action is, the first transition is that the start switch is pressed, right? You press the start switch, you try to everyone must have operated with your washing machines. You try to get that analogy back. You switch on the washing machine. Now you have allowed your drum of the washing machine to get filled with the water. So therefore here your first step or whatever the action that is taking place is identified by a value called drum. The drum is the thing which I am interested in the first transition, and I wish to see whether the drum is filled or not. Whether the drum is filled or not is the action, that is the output which is taking place. So now this point, that is fill with water. If you want to make the drum to be filled with water, you should have some water input here and maybe a kind of switch. Maybe it is the tap in my case, in this particular case. Okay. So now I need to fill the water. There should be a water level indicator here which operates once the water is filled with the desired amount of water, right? And that serves as the second transition or the input for the second step or the transition in the second step. That is level indicator, the water level indicator. I hope you are following this. Okay, so now this is the start switch. Here I will write it as SS, and now here I have WLI, which is the water level indicator. So now to this stage wherein the water is filled with the required amount. Now that serves as the second step. Now in that case variable here, okay, or the field is water. Now what action you are going to take here? Now heat the water, right? You have to heat the water. In order to heat the water, maybe you devise one more switch. There may be some other switch which takes care of heating the water. So now the water is getting heated here. Let us say that I wish to heat it up to say 40 degree centigrade, right? Now temperature switch. So this serves as the third transition after having got the output from the previous one. Recall the previous diagram, right? So when I have got out 0 and in 1 serve as the inputs to your out 1, correct or not? Or I have taken it as out 1 in 1, that will serve as the input for your out 2, if it is like that, right? So therefore the heated water here, temperature which is reached, right, or the hot water is the third variable here. What you, right, first is the drum, second one is the hot water, now the third one is the hot water. So now when you have the hot water at a desired degree centigrade, then you will have to start the washing machine. It will rotate for say 15 minutes. How do you come to know that it has rotated for 15 minutes? You will have a time switch here, right? It will come 14, it will come 13, so on and so forth. Once it becomes 0, it will initiate some action. Now, cycle means in my particular case, it is going to stop here. If you have any other cycles, maybe drying the clothes, okay, so once 15 minutes, for 15 minutes if it has run, you may have to turn on a dryer so that the clothes are dried inside the drum itself for 10 minutes or 5 minutes, something like that, right? So there you may have the subsequent, okay, so now that I could be able to draw somewhere here time switch. So time switch, you will go to say a dryer. It was not there in my problem statement, please note it. Since it is written, I am adding some more attributes to your washing machine here. Dryer, okay, again from the dryer you might have one more switch, time switch. You may have one more time switch, right? So now this is taking you to stop or open the door or something like that, right? So that you manually have to remove and you have to put it for the other purpose, right? So now these are the different steps that execute whenever you want to have a sequence of operation, right? Could it be of the traffic light type? Could it be of the washing machine? Could it be of any industrial process? I will give you some problems later. You will have to devise your sequential function charts, and also you have to draw the subsequent ladder diagrams, right, for some of the simple industrial processes, right? Later we will have them as the assignments and all, but please try to understand the concept here. Start, then some action or some transition, and that transition is for what? That is the action word there. Could it be drum? Could it be water? Could it be hot water? Could it be a dryer or something like that, right? Then what has happened in each action? The water is filled to the required level, then the water is heated up to the required temperature, the drum is rotated for the required period of time, the dryer is turned on for a required period of time. So when all these operations take place sequentially, so finally you have to have a stop command. Once you have a stop command, the entire operation gets over, right? So if it is a continuous process, then probably you may have to go back to the start. You need not necessarily always go to the start command. Somewhere in between also you can go, depending upon the type of the operation that you are going to carry out there, right? In this way, it is possible for us to have the application of the sequential function charts and how we should be able to draw the ladder diagrams for the sequential function charts in the specific applications. All the operations here, if they are to follow a particular sequence, then it is possible for us to draw the sequential function chart. Okay, I hope this is understood by you, and now we will try to see some of the possibilities that you can have in the sequential function charts, or the operations which are required to be conducted in a sequential manner. So the first one, we call it as selective branching. The first one is referred to as selective branching. So now these kind of operations are very essential. Again, I repeat, in the industrial control or the sequential process of operation, right, or the process control. Now, what exactly we mean by selective branching? State 1 occurs if the transition condition IN1 occurs, but the state 2 if IN3, then state 3. Please note this. I have got one state.
Or state 3, apart from having the output 0, you will have to selectively have some other input stages. Okay, now you have turned on the MCB. Okay, if you want to turn on the light at hall, the corresponding switch has to be turned on. If you want to turn on the light in the corridor, the corresponding switch has to be turned on. If you want to turn on the light in the kitchen, the corresponding switch has to be turned on. It is a very simple analogy for what we have taken. MCB is turned on. Unless your MCB is turned on, it is not possible for you to turn on any one of the lamps which I have mentioned, right? So if you want to turn on the lamp in the hall, apart from turning on the MCB, you have to turn on the corresponding switch, and then only the light at the hall will be turned on, and holds good for the other two cases. This is very, very simple for you to understand. Okay, this is called as selective branching. Any state occurs if and only if one of the previous state and the corresponding inputs for that state fulfills or holds good. That is called as the selective branching. Now, once the selective branching is known in terms of the SFC, so you should be able to draw the corresponding ladder diagram. Okay, so now the first state here, okay, I start with the output 0 only, because this is okay, this is already there. Otherwise you can always have one more rung also here. Please note something like this, right? So this is also possible. This is my out 0, and this is, let us say that this is my in 0, something like this. Okay, because that is not mentioned, so I can definitely start with the output only. Okay, so now if you look at this rung here, okay, if you look at this rung, in1 and out 0 will result in state 1. State 1 would be resulted if and only if both out 0 and in1 are true. State 2 output is possible if and only if when out and in2 are true. State 3 output is possible if and only if out and in3 are true. That means in order to have the individual outputs out 1, out 2 and out 3, out 0 is a must, plus means and in1 and in3. So this kind of examples also you will have to come across later. Okay, so this is called as the selective branching. So now maybe the same example which I have just shown you, the washing machine example. One second. That is also an example of the selective branching. Now you have the parallel branching. One is the selective branching, another is called the parallel branching. Okay, so in parallel branching, what you see, what changes you can see apart from what you have seen in our previous case, that is the selective branching. See here, state 0, out 0, then after out 0 you have got in 1, there is one more transition, and this in 1 results in simultaneous outputs of state 1, state 2, state 3 and corresponding to their outputs. So this is very similar to having
three different appliances turned on by one particular switch. That's what you can take, right? So I have got one main switch. When I turn it on, the three different appliances getting simultaneously turned on is represented by the parallel branching operation. When input 1 occurs, then the state 1, state 2, state 3 all are simultaneously realized. Of course, it is from the pre output state. You can see the corresponding ladder diagram here. Out 0, and again in the similar way you can have one more rung added here. So this is my IN0 and this happens to be my out 0. This is IN0. Okay, so that is only an optional one for you. Now what I will out 0 along with IN1 results all these three things simultaneously. So therefore these three must come in parallel. So this is called as the parallel branching. Selective branching is one and another is parallel branching, right? Then you have something called as the convergence. Please look at this: selective, parallel branching, and the next one is the convergence. Now you can see here state 4 follows when either IN4 or IN5 occurs. So this is the meaning of the convergence. If at all you want to have state 4, either IN4 from your state 2, IN5 from your state 3 occurs. So now see here, state and IN4, they happen to be one input when both happen, when both are ANDed, right? That is one case. Apart from that,